Welcome back, everyone. We will continue in this lecture with a few examples of reinforcement learning. The idea here is trying to motivate all of you why we need to study reinforcement learning. So let's look at some of the popular examples. So before we get started with the examples, I'd just like to give a few acknowledgements for the contents of the slides. So the first one is a very excellent lecture series by Professor David Silver, who's currently working at Google DeepMind, and from the Reinforcement Learning and Introduction textbook. So let's get started with some examples. Okay, so the first one is related to board games. Historically, a lot of the research in reinforcement learning has been applied to board games because they are very good examples of decision making, right? Now, backgammon is a particular board game where every player has some coins, maybe 15 coins. Every player has 15 coins, and the objective of the game is for each player to move all their coins from a starting point until they come to the end point, right? And now the game of backgammon has some concept of randomness because they have to roll a dice, and then there is also some strategy which is required by the players. So in this study by Tesaro, so reinforcement learning, specifically temporal difference learning, along with using a neural network as an approximator, was used to solve the game of backgammon, right? And one interesting thing to note over here is this game was, or rather, this algorithm was trained entirely from the agent playing with itself, with another replica of itself, and through self-play, the agent got better and better at playing the game. So through sort of a trial and error process, the agent learned how to play the game of backgammon. And the agent has gotten so well to an extent that it started playing some moves which humans have never tried before. And actually, when this algorithm TD Gammon came out, some of the expert players actually came up with new ways of playing the game of backgammon. So this is one very good popular example of backgammon, or like reinforcement learning applied to board games. Now, changing it to a context a bit. So in this example, reinforcement learning is applied to a robotics use case. So as you see in these images, the objective of this problem statement is trying to autonomously fly an helicopter, and not just to fly an helicopter, but rather to do very difficult maneuvers. So the image on the right shows a human using a remote control to actually fly the helicopter. And typically it's a very difficult task, and a human has to train over a significant amount of time to actually do this task. Now, in this study, what the researchers have done is they have asked a human to fly the helicopter and use that data to build a model of the environment. So what this means is they tried to build a machine learning model which sort of predicts what the helicopter does when a certain control command is sent to the helicopter. And then based on this model, by using reinforcement learning, they were able to train the helicopter to do very complicated maneuvers, right? So if you see this video, so the helicopter has learned to do maneuvers where it's flipping in the air. And by the way, these are the main researchers who worked on this topic. And the helicopter actually learns to do very complex maneuvers, right? So this is an example of applying reinforcement learning to a more real world setting such as robotics. So these are some classical examples of applying reinforcement learning. And when I say classical, what I mean here is Typically, reinforcement learning algorithms use some model or function to approximate what the algorithm learns, right? Or approximate some component such as a value function. Now, when I say classical, what I mean here is like using small scale models or very small neural networks to solve the problem. Now, when we switch to some of the modern examples, in all of these examples that I'll cover moving forward, the function approximation is actually done using a much larger model, such as like a deep neural network, right? So let's look at the first example. This is again an application of reinforcement learning to a board game called Go. So now the rules of Go are very simple, right? So there are two players. There is a player with white coins, and then there is a player with black coins. And the coins can move to different positions on the board following certain rules. And the objective of this board game is trying to capture as much territory as possible, right? So let's say if there was some region where there are white coins surrounding it, then this entire region of the board belongs to the white player, right? So this is the objective of the board game Go, which doesn't have very complicated rules. But the problem with Go is that this is a board which has a lot of possible positions and a lot of coins. So the search space or the possible set of actions that a player can take is very huge. And to any traditional algorithms that were applied before usually weren't possible to be applied to Go. So in this particular study, which was from Google DeepMind, so they combined existing reinforcement learning algorithms with using deep neural networks to do the function approximation. And they were actually able to solve this board game very efficiently. And also, this image that we see on the right is where the algorithm AlphaGo beat the world champion Lee Sedol. Now, in this particular study, there was some pre-training that was involved where based on human expert moves, the neural networks were initially trained and then reinforcement learning took place. But then a later variant called AlphaGo 0 started with self-play where there was no input from human expert and the agent learned by itself, and then it became even better than the AlphaGo algorithm which was released earlier. So again, in this example, the algorithm AlphaGo 0 and AlphaGo came up with such new strategies that humans have never seen before. And it actually changed how humans are now playing the game of Go. So what this again shows is when an agent learns through trial and error, through its own experience, it can gain much more superior strategies than simple supervision coming from expert moves. Okay, so now another modern example is where a reinforcement learning algorithm plays the retro games, right, or video games. So again, this is something that has been done before, but usually what happens is the agent, or let's say there is some pre-processing step where the raw input that comes from the video game is pre-processed and certain features are extracted, and those features were provided as input to the reinforcement learning algorithm. But again, in this example, a deep neural network was used, and the raw image that comes from the video game and then the raw score that comes from the video game was provided as the state and reward to the agent. And because of the power of a neural network, it was able to extract useful features by itself and then learn to play the game efficiently. And another very important achievement of this paper is that the same framework of using Q-learning was sufficient to decently or play the game at a superhuman level for most of the Atari games, which was maybe a difficult thing to achieve with earlier reinforcement learning algorithms. So again, let's look at a video demo of this game. So a very one of the common games that we see in Atari is this game of Breakout, right? So what we see here is how the agent is learning over multiple attempts at playing the game. So initially, the agent loses the game after breaking a few tiles, right? But then, as the agent learns more and more, it starts getting better and better at the game. And then, in one episode, which is like playing the game once, the agent is actually able to break more and more tiles. And beyond a certain point, again, the agent is able to discover a very efficient strategy at winning the game. So one such strategy you can see right now. So the agent figures out to break the tiles to one side of the window and send the ball there so that the ball automatically breaks a lot of tiles. So again, through this idea of doing trial and error, the agent is actually able to discover very efficient strategies at playing the game. And maybe humans who typically play this game may not be able to discover such strategies immediately. Okay, so this was and here is another modern example. So this is an example where researchers are trying to teach motor skills, or rather visuomotor skills, to a humanoid robot. Now, the classical way of doing this problem is usually there is a pre-processing algorithm which extracts a lot of features from the image that the robot sees, and then there is very careful planning based control which happens for the robot to actually do the task. But in this particular study, there is a reinforcement learning agent which receives the raw image as input, and the agent tries to solve the task directly by processing the input images without requiring multiple algorithms to solve the task. So again, if we look at this video demonstration, so there is a model which has like a deep learning based architecture where it's able to extract important feature points from the environment, and then it directly outputs the torques that the robot has to output and directly move the arm rather than having an actual planning algorithm, right? And again, just like the Atari example, the same framework, the same policy search based framework was sufficient to solve multiple robotics tasks. So it could solve tasks such as hanging a hanger, or like putting objects inside a cube and things like that. So as you can see here, by combining reinforcement learning with deep learning, we are actually moving towards robots which are generalized and able to solve multiple tasks at the same time, or using the same framework. Okay. And then I think all of you are seeing a lot of hype around large language models and a lot of very interesting use cases coming out of language models. Now, one of the common use case of language models is this chat interface, right? Where a human can ask any question to a large language model, and then it outputs some text which tries to answer that question, right? So chat GPT is a very popular example. Now, ChatGPT, or rather the GPT models that are trained, right, are trained using a lot of tools. But one of the very important tool is also based on reinforcement learning. It is based on this idea called reinforcement learning with human feedback. So the key step here is focused on step number 2. So um, reinforcement learning agents require a reward to understand how to act in the environment. So here, for training large language models, a reward model is trained based on human preferences. So many of you might have noticed when interacting with ChatGPT, sometimes you get a prompt saying, do you like this answer? Or do you like option 1 or option 2? So whenever you pick a preference, you're actually contributing to training a better version of ChatGPT. So all this data is aggregated by OpenAI or any other vendor, right? And all of this data is used to train something called a reward model. And then when actually training the agent, this reward model is used to provide some reward to the response that the agent generates. And then using this reward, the model can train itself at generating better and better responses. And this is one of the reason why we really like interacting with ChatGPT or some of the other variants, and why it is able to generate such helpful responses. So based on this video, you might have gotten an understanding of the many use cases or many applications of reinforcement learning. And we believe that there would be more and more use cases coming up in the future, and it being a very important topic to learn and implement in the real world. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.